So chapter 7 begins with the rotational kinematics. Okay, 3 terms you have to know. The first term, angular displacement. So angular displacement is like this. So imagine this wheel here, this bicycle wheel. So see this point right there? So imagine that this bicycle wheel makes one complete revolution. Bam. The bicycle wheel makes one complete revolution. That would be an angular displacement of, we could say, 1 revolution. But what else could we express the angular displacement in? Radians. We could say 2 pi radians. And then there's a third one, 360 degrees. So these are your conversions, which you're going to need. You're going to need these. Hey, leave them alone. You're going to need these for your rotational kinematics. So what if the bicycle wheel made 2 revolutions? So if the bicycle wheel goes around twice, that would be an angular displacement of 2 revolutions, 4 pi radians, or 720 degrees. So basically, angular displacement is how many times the object rotates around, expressed in revolutions, radians, or degrees. Now, angular velocity. So say, for example, that this bicycle wheel makes an angular displacement of, let's just say, 2 revolutions, and it does so in a time of 1 second. Could we talk about the motion, the velocity of this bicycle wheel in an angular way? Not in a linear way, like, in a linear way you'd be talking meters per second, but could we talk about this in terms of like degrees per second, radians per second, revolutions per second? Yeah. So what would this be? So the angular displacement is 2 revolutions, and the time was 1 second. So this would give us an angular velocity of 2 revolutions per second. Does that make sense? Now what I want you to know about angular velocity is that this point on the edge of the wheel and this point, which is closer to the center, these 2 points have the same angular velocity, right? So like what we know about this point, the angular velocity is 2 revolutions per second, meaning what? Every second it goes around twice. The same thing has to be true for this point that's closer to the center. Both of these points share the same angular velocity. Can you wrap your brain around that? If this point goes around twice in 1 second, then this point goes around twice in 1 second. Okay? Now, angular acceleration. So let's say, give you an example. Let's say that this bicycle wheel starts at rest. The initial angular velocity is 0 revolutions per second. Starts at rest, and then the final angular velocity is 6 revolutions per second. That'd be really moving. 6 times around in 1 second. And say that all takes place in a time of 2 seconds. The time there is 2. So, is there an angular acceleration? Yeah, because the bicycle wheel starts from rest, and it goes faster, 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 faster. It speeds up. Okay, so what's our change in the angular velocity? The angular velocity goes from 0 to 6. So what's the change? 6. And how long did that take? 2. So this ends up being 3 revolution per second squared. Now what the heck is a revolution per second squared? Well, all that means is 3 revolutions per second every second. Every second, the bicycle wheel is spinning 3 revolutions per second faster. That's all it means. Revolution per second squared. Now guys, here for this whole first part I talked about revolutions per second. Do you have to be in revolutions per second? No. Do you have to be in degrees per second? No. Do you have to be in radians? No. The thing you got to pay attention to is making the units the same. And there is one equation where you have to be in radians. I'll talk about that later. All right, next screen. Okay, the linear kinematics and the rotational kinematics. At this point in the class, everybody in this room should have the linear kinematics memorized, because you use them like in every chapter. X equals 1/2 at squared plus v initial t. Vf equals v initial plus at. These are the motion equations. Now, the rotational kinematics, the point I want to make here is that these equations are the same as the linear kinematics. These four equations up here are identical to these four equations down here. Okay, but what happened? Your linear displacement is now changed to angular displacement. Your linear velocity is now angular velocity. Your linear acceleration is now angular acceleration. Okay? You don't need to copy this down because it's in the Spaldo notes. If you want to copy it down, I'll leave it up for a minute. You guys want to copy it? It's in the Spaldo notes. Okay. So let's try these out. Okay, the rotational kinematics. We have a problem. It's a real easy problem. This should take you like 2 or 3 minutes to solve. This washing machine starts from rest. What does this tell you right here? From rest. What is that telling you? Angular velocity initial is 0 revolutions per second. Oh, and like I said with the units, when you're using these rotational kinematics, is there any unit that you have to be in? No. What's the key thing you got to do though? Make sure that whatever quantities you're working with, be it degrees, be it seconds, be it hour, whatever it is, you want your units to be the same. So for example, if you had a displacement that was like 2 revolutions, and then you have an angular velocity that is 6 radians per second, are these going to work together? No. So you just got to make sure the units agree. The units agree. All right, so I'll give you guys 3 minutes. Read this problem. It's just rotational kinematics. All right, so here's the info we have. So the washing machine starts from rest. This is a real easy problem. 0 revolutions per second. It speeds up to an angular velocity final right here. 2 revolutions per second. That all takes place in a time of 3.5 seconds. So I just want you to get the feel for rotational kinematics. So the first question, what's the angular displacement? We don't have that. Theta, angular displacement's a question mark. Acceleration, alpha, that's a question mark. So how do we find the angular displacement? Could we use the first equation? No, because we don't have the acceleration. So let's look to the second one. Will this one work? Yeah. So we go theta, our displacement. Oh, and it's understood to be delta. Technically it should be delta theta. So delta theta equals 1/2 angular velocity final, angular velocity initial times t. What's the initial angular velocity? 0. So this is our displacement's going to be 1/2 angular velocity final is 2 revolutions per second. The time is 3.5 seconds. The seconds cancel, and we get a displacement of 3.5 revolutions, which could be converted to whatever you want it to be. You could convert that to degrees. You could convert it to radians. Like if you're on a multiple choice test and the answer choices are in degrees, then what do? You go, okay, 1 revolution is 360 degrees. If they wanted you to convert to radians, then the numerator would just be 2 pi. Okay? All right, so we got the angular displacement. Now, make some room here to get the acceleration. Which kinematic does it? We could either do the third one or the first one. Both of those are fine. Or even, Hey, even that one, we have 3 of the 4 that would work. I like this third one. Angular velocity final equals angular velocity initial plus alpha t starts from rest. So the angular acceleration is going to be the final angular velocity divided by the time. So that is 2 revolutions per second divided by 3.5 seconds, which gives 0.57 revolutions per second squared. What is revolution per second squared? Well, that means 0.57 revolutions per second every second. Every second, the washing machine is rotating 0.57 revolutions per second faster. Revolution per second squared. All right, final thing for the day, and this is where we're going to pick up tomorrow, is tangential velocity. Now, tangential velocity, it's not an angular velocity. This is a linear velocity. So what will tangential velocity be measured in? Meters per second. It's a linear velocity, but it has to do with rotational motion. So the best way to put your brain around tangential velocity is imagine a speck of dust on this bicycle wheel. If that speck of dust flies off the wheel, so say the bicycle's in motion, if this speck of dust right here flies off the wheel, how will it leave the wheel? Tangent to the circular path. What if the speck of dust flew off right here? How would it leave the circle? Tangent to the circle. What if the speck of dust left right here? What if it flies off right there? How does it leave the circle? Tangent to the circular path. Now, it's a linear velocity. It's in terms of meter per second. If we compare 2 points on the wheel, just like we did with angular velocity, so say we look at a point here and a point that's closer to the center, right there. Do these 2 points have the same angular velocity? Yeah, so for example, if this point is rotating at 1 revolution per second, then this point also is rotating at 1 revolution per second. Does that make sense? But how about their tangential velocity? See, tangential velocity is in meters per second. If you compare a point out here and a point closer to the center, which of these 2 points has a larger meter per second velocity, linear velocity? Which one's traveling faster? The one on the outside. And here's why. If you think about it, so both of these points have to get around in the same time, right? Both of those points have to make it around in the same time. Which point is traveling a farther distance? The inner point or the outer point? The outer point. So that brings us to this equation right here. One way to get tangential velocity is you take the angular velocity and multiply it by r, which is the distance from the center, the radius. Now, this angular velocity, when you're using this equation, this has to be in radians per second. It has to be radians. Okay? Now, the other way to get tangential velocity is you take this equation. Now look, what's 2 pi r? 2 pi r is circumference, and then what's capital T? Capital T, it's a time, it's called the period. Now what is period? Once a month, Spaldo gets in trouble. Right, it's the same sort. That's not true. It really is not true. But look, there's the biological period, and then there are physics periods. And what do we mean by physics period? Well, look, this wheel spinning around. Well, what's the definition of a period? Be it a biological period or a physics period. Period is the time for one cycle. It's the time for one cycle. So what's the cycle happening here? It's the circle, right? One cycle, 2 cycles, right? One complete circle is the cycle. Other things that have periods in physics, pendulum. What's the period of a pendulum? One complete cycle. They're back. A mass on a spring, going up and down. Mass on a spring going doing, doing. The period would be the time for one complete cycle. Waves. Final thing is waves. What's the period of a wave? The time for one wave. Okay, so look, if you take the distance around one circle, which is the circumference, and divide by the time for one circle, that's the tangential velocity. And by the way, where does this equation here come from? Where does this come from? Velocity is, you take the distance around one circle, the time for one circle, that's the velocity.